hopefully next week it will be ready, otherwise Olivier is gonna kill me. So this is about reducing a metabolic model and using to optimize the consumption of organic waste. So the idea is to couple the production of microalgae with the dark fermentation. And dark fermentation is a method that is widely used to treat waste, various kinds of waste, agro-industrial and also wastewater. And it's also a renewable source of hydrogen. But the problem with dark fermentation is that it has volatile fat acids, and we also have to treat this product of dark fermentation. So the idea is to couple this with microalgae that can consume them heterotrophically or mixotrophically. So we can also produce biomass and treat the wastewater. The main problem with the volatile fat acids is that we have the butyrate. Mainly we have the butyrate and acetate at the end of dark fermentation, and butyrate is the predominant. I think it's about 70% of butyrate. And there are two kind of problems. First is that the acetate inhibits the consumption of the butyrate, and also butyrate, if there is too much, the consumption is also inhibited. I'll show after the kinetics. But one solution to this problem is that we can add another substrate, or also we can grow the microalgae with lights, so we have a mixotrophic growth. This way the microalgae can grow faster, and then we are going to consume the butyrate and acetate faster. So here we're going to work with a metabolic model for Chlorella sorokiniana. Yes. And we are going to use 4 substrates together with light. And we're going to have the acetate and butyrate. They are coming from dark fermentation, and the glucose and glycerol there we're going to add, so it can make the microalgae grow faster. And in a metabolic model, we have a chain of reactions that consists of hundreds or thousands, depending on the model. And at the end, we're gonna have some product. So because it's a lot of reactions and metabolites, if you're gonna to optimize, it's better if you reduce the model. So a general description for the metabolic models is in this way: differential or ordinary equations, where we have the substrates, they are outside of the cell, they are in the medium. Then you're gonna have some intracellular metabolites, they are represented by C. Then you're gonna have some products that are gonna be excreted by the microalgae, and also some biomass, they're going to be produced. V is the vector of kinetics reaction, the rate of reaction. And K is the stoichiometric matrix that comes from the chemical reactions that describe the process. So in general, to reduce the metabolic models, we make the assumption that the internal metabolites are in a steady state. So the derivative of the intracellular metabolites is 0. So we're going to have this equation K times V equals 0. And mathematically means that the flux distribution, they are non-negative vectors belonging to the kernel of the matrix K. So this means that the vector of fluxes, they can be represented in this way. And by using this technique that we call the elementary flux modes, we can kind of reduce the metabolic model. So here we have an example. This is just a toy metabolic network. So the idea here is to find the elementary flux modes. There is a mathematical definition that it can also change. Some aspects of it can change depending, depending on the definition, they call it a different way, not elementary flux modes. But the idea in general is the same. We're gonna have some steady state chain of reactions. They're gonna represent the consumption of substrates into the product. So here we have one FM. We're gonna consume the substrates S2, S1, and produce the product 2. So here is actually just one reaction, the C2 and C3, they produce P2. Then you're gonna have another elementary flux modes. So this is a steady state reaction, the substrate 2, that can produce the first product. And then we have a third elementary flux mode, that from S1 to P1. So the idea of the EFMs is that we can construct micro reactions. So with the first elementary flux mode, you're gonna have the micro reaction S1 plus S2 produces P2, and also for the other two elementary flux modes. But the problem is that for microalgae, the internal metabolites, they vary, the concentration varies, it's not a steady state. So for example here, the carbohydrate carbon content, it's during at night, since the microalgae is going to use respiration and there is no photosynthesis, the carbon content diminishes, and then during the night, because of photosynthesis, the carbon content increases. So one method that was developed by Caroline, her thesis, is that we divide the metabolic network in subnetworks. So instead of just having just one network, they're gonna compute the elementary flux modes. We're going to divide them, separate them, and take some metabolites they're going to accumulate. For example, here we could assume that C4, again, it would accumulate. Then you're gonna have some elementary flux modes. There will be S1, C4, and then C4, P1. So this is the reduced metabolic model. First we have almost 200 reactions and metabolites, and by applying that method we end up with 7 macro reactions, 2 intracellular metabolites. There's the GAP and substrate, and also the 4 substrates, both butyrate and acetate, that comes from the direct fermentation, and then glycerol and glucose they're gonna add. So this is the kinetics of all of the reactions. So as I said before, the problem is the butyrate. where we have the equation that Olivier showed Monday, I think. So there is an inhibition because of batch rate, and also an inhibition due to acetate. So for other reactions, we use just mono. Only for the internal metabolites, it's a linear reaction. And here, because it's a maxotrophic model, we have the light that uses also we consider the attenuation of light because of biomass. There are many ways of modeling the maxotrophic growth, but here I consider just the simplest case that we take the sum of the phototrophic growth by light and the sum of the heterotrophic growth.
I'm sorry. Why did you choose these reactions? How did you decide, for example, to take one Michaelis-Menten or to take one linear one? How is the choice?
So, yeah, I think so. This is actually something that I'll talk later, because tomorrow I'm going to model it for some experiments in the literature, and the problem is that, for example, glucose and glycerol, there is inhibition, but the problem is that the papers are not very well done, because sometimes they have a nitrogen limitation, and we cannot actually know when is the inhibition, but I'll talk about it later.
Maybe just if I can add something. The general rule is that we try to be as simple as possible, so linear for most of the reactions.
I think.
Except the ones for which you have uptake, where you use Michaelis-Menten kinetics. And for butyrate, it's a bit different because of the inhibition. But basically, it's linear except for the absorption.
Okay.
So this is the metabolic model fitting some data for experiments that we found in the literature. Here we have just the batch rate and microalgae. This is also a maxotrophic growth. And the model works even with two substrates. Here, for example, there are many experiments, like here, that actually the substrate is not all consumed. For example, here we have some glucose that there is still in the medium. So this is a Taylor diagram that we fitted. So we simulated the model for 122 experiments. So each point is one experiment, and this is the Pearson correlation. So the closest one, the better is the model. So most of the experiments, the model is very good, although there is some experiments that doesn't work at all.
But what do you call experiments?
For example, in one paper, you're gonna have an experiment with 10 grams of glucose.
Okay. So
this is one experiment. Then the same paper, they're gonna have an experiment with 5 grams liter of glucose. This is another experiment. I think there are about, I don't know exactly, but it's between 10 and 20 papers. I think all the data.
And just to make it clear, obviously, all these are playing with the same parameters.
Ah, okay.
Yeah. It's not straightforward.
No, okay.
So here we apply the model to real problem in the about dark fermentation. So a general concentration that we can find at the end of a dark fermentation process is 3.5 butyrate and 1.7 acetates. So as you can see, the butyrate is the problem, and also it's the Peyresq that is more present. So to optimize, here we are gonna try to optimize the time to consume the substrates, and you're gonna use that as condition the chemical oxygen demand. So we take a value from the law here in France. For fluxes higher than 100 kilograms per liter, you have to limit the demand in oxygen by 125. So the idea of this is that we are gonna oxidize the substrate until carbon dioxide and water, and you're gonna have a demand in oxygen to oxidize each substrate. So for example here, glucose, you're gonna, the maximum limit you're gonna have is 0.1, and butyrate is the one that we're gonna have to clean the most, so it's the most problematic. So here's what I was gonna talk, that I have a lot of problems to model, is because especially although for the experiments it works to model the experiments, but concerning optimizing the time, if we just use the mono equation to simulate the consumption of glucose or glycerol, the optimizer will just try to increase the concentration of glucose. They're just gonna add a lot of glucose, so the microalgae will grow at its limit. But the results are not very realistic. For example, using the mono equation, we find the optimal glucose concentration about 200 grams per liter. Although it's possible to do something like that, I don't think it's really the optimal. For example, but what I was going to talk is that in the literature, there are some results that don't quite fit. So here we have an experiment with different concentrations of glucose, and the maximum productivity that we have is about 10 grams per liter, and when we increase to 25 here, you can see there is a kind of inhibition, and we try to make some hypothesis why this happened, and in the end, like consumption of oxygen, but in the end it's very probable that it's just the nitrogen that is limited. And I think here maybe because we have more glucose, that we have more problems. In the experiment they have more problems with contamination. So that's an idea. But while in this experiment we could say that 10 grams per liter is the optimal glucose concentration, here we have an experiment at 80 grams per liter of glucose, and here we have with this concentration we have the best productivity. And also here, this is fixed glucose concentration, and also using different nitrogen concentrations. So clearly here we have limitation by nitrogen. Although sometimes more nitrogen we put, less is the final concentration of biomass. Well, so according to the literature results, we could say that the best glucose concentration would be about 80, between 60 and 100. So here I consider an inhibition. I kind of cheated a little bit concerning the optimal concentration of glucose.
What?
No, but this is actually calculated by the optimizer. What I cheated was the parameters, so I have to recalculate this. But considering the inhibition, we have a value that is realistic, let's say, concerning the literature, of 60 grams per liter. And using this adding this concentration to the end of the dark fermentation, we can consume and be inside the law, or under the law, in almost 5 days. And as you can see in this graphic, here you have the glucose concentration, and this is the time to consume the substrate. And if you don't put any glucose, we actually have like more than a month to consume all the butyrate and acetate. So clearly adding glucose is a very good strategy to reduce the time and optimize the coupling system between dark fermentation and microalgae. So next, what I'm going to try is to also add a criterion of price, not just the time, and also mix the glycerol and glucose. So I think that will be done next week. That's it.
Thank you.